So in this talk, we are going to cover some key performance indicators and also look at why we really need evaluation metrics. So intuitively, the reason is same as why students need or employees need evaluation, right? Employees and students are evaluated by the key performance indicators, and similarly, machine learning algorithms also are evaluated based on their performance. So recently, generative AI particularly has been achieving human level effectiveness in various domains. The powerhouse of generative AI today is machine learning. Most of the artificial intelligence is anyway driven by machine learning. So in terms of the performance, machine learning is achieving similar performance levels as human beings. In fact, the level of multimodal understanding of text, images, and audio is both surprising and unexplainable. In fact, GPT-4o demonstrated some amazing emotion understanding and generating abilities as well. So in terms of text summarization, machine translation, question answering, code generation, image captioning, speech recognition, in all these areas, generative AI, which is driven by machine learning, is achieving tremendous performance results. But how do we know for sure that it is achieving all this? We know this only by measuring its performance quantitatively, right? We don't want subjective evaluation. We want quantitative evaluation of the performance. So there are some quantitative measurements of performance. On this slide, you will see some benchmarks that are typically used with these large language models. For instance, MMLU stands for Measuring Massive Multitask Language Understanding. And GPQA stands for Graduate Level Google Proof Question and Answers, and things like that. And as you can see, GPT-4o has achieved really remarkable quantitative measurements in all these benchmarks. In fact, uh, large language models are passing some tough exams as well. You would have all been following news. Um, so ChatGPT passes exams from law and business schools. This is the headline from CNN, and another headline: GPT-4 scored in the 90th percentile of the business school exam with a score of 298 out of 400. And USMLE, the ChatGPT passed all three parts of the United States medical licensing examination within a comfortable range. And GPT-4 is the SAT reading and writing section with a score of 710 out of 800, which puts it in the 93rd percentile of test takers. So another way to measure the performance is to make these machine learning models take the same exams as human beings and measure the performance like we saw on this slide. But in spite of all these commendable results, quantitative measurements, why are the large language models unable to replace lawyers? Or for that matter, doctors, because it has passed the medical licensing examination as well. The reason is because numbers can be misleading. So here's a caveat. So in a recent paper from Apple, these researchers from Apple in October 24, just a couple of months back, they published this preprint. They posted this preprint. So where they say that we investigate the fragility of mathematical reasoning in these models and demonstrate that their performance significantly deteriorates as the number of clauses in a question increases. We hypothesize that this decline is due to the fact that current LLMs are not capable of genuine logical reasoning. Instead, they attempt to replicate the reasoning steps observed in their training data. So it's like an open book exam with answers clearly marked. So the models store the information. So you take the bar license exam, for instance. Most of the questions in the bar license exam would be available online somewhere, and the answers as well available. And these questions and answers are all in the model that the large language models are typically, right? Um, so it's as good as an open book exam with all the answers marked. So these benchmarks are kind of a bit misleading. So it is not anytime soon that these models, large language models, or artificial intelligence are going to replace lawyers and doctors. But in spite of their limitations, we still need some ways to measure performance. Just like we know student grading is not perfect, but we still need to evaluate their performance. One reason is to give some idea about their own skill set. I mean, we need to give students feedback, right? So that's one reason, which probably does not apply to the large language models. But we also grade the students to um, tell the world know, let the world know about their skill set, right? I mean, world in the sense the students' world, not our world. Wherever they want to use the grades, we want the recipients of the grades to understand the skill set that the student has acquired through the program. So for similar reasons, we need to continue to evaluate quantitatively the machine learning models. So a little bit of more motivation. Why do we care for accuracy? Because every small decimal point percentage pays. So I got this anecdote from a couple of anecdotes from this website called Data Robot. Um, so a few months back, they claimed that just a 1% reduction in registered nurses' hours paid per patient day netted $2 million in savings per year for just 8 of the 38 hospitals in Stewart's network. So apparently, Data Robot was employed in Stewart's network, and they saw that a 1% reduction in the prediction. So basically, Data Robot is a tool which runs several models. It gets thousands of models. It evaluates the data set on thousands of models and tries to do the best in its prediction, tries to find the model that works best for the prediction. So in this case, the prediction is that of the registered nurses' hours paid per patient day. And a 1% improvement in the accuracy resulted in $2 million savings per year. Similarly, reducing patient length of stay by 0.1% resulted in a saving of $10 million per year. So if you predict the patient length of stay with a 0.1% improvement in accuracy, you can save $10 million a year. So, uh, so that is the idea. We proactively predict the various parameters, controllable parameters, to reduce costs in case of healthcare. So accuracy really matters a lot. So let us start by looking at the very essence of how we evaluate performance of these machine learning models. So let us take the classical case of binary classification for which um, machine learning models are used. So typically what we have is a ground truth, which is used for training the models or generating the models. So this ground truth in traditional machine learning is a table with the columns representing the features and the rows representing the instances. The instances could be people, could be anything. Um, so in case of a class, the rows indicate the um, students, and the columns represent the assignments in which the students score. And the last column is special in that it is a target variable. It's a label. Because this is a binary classification, the labels could be positive or negative. I mean, just for simplicity, the classes can be anything, but just for ease of understanding, let us think that the classes are either positive or negative, P or N. So what is done is we split the ground truth, the data set into two tables. One table is called the training data, and the second table is called the validation data set. So we split the ground truth into two tables, training and validation, or training and test. Um, So from the training data, we use a machine learning algorithm to generate a classification model, right? We generate a classification model to, to do the predictions. So the classification model is typically a set of weights or parameters, weights assigned to each of these features. The weights are also called as parameters. When you say that the large language model ChatGPT has 175 billion parameters, it simply means that there are when you download the file, it's a series of 175 billion floating point numbers. So that is the model. How to use these numbers is controlled in a program, a small program, maybe a few hundreds of lines of code. Um, uh, does the inferencing part, right? So using the machine learning algorithm, we generate this kind of a model, and then we pass the validation part of the ground truth of the data set to the classification models to obtain predictions of the classes. So we already have the classes, the actual classes in the validation data set, but we pretend as if we don't know the classes, and we predict the same column using the classification models. And then we compare the classes, the actual class with the predicted class. And once we compare, we know how good the model has performed in doing the predictions. So that is the idea of binary classification, and that is how we measure the performance of the model in a very high level, at a very high level. So we compare the actual class with the predicted class, and see how many of the uh, rows the class was correct. So that's how the performance is measured. So how many possibilities of the machine learning model performance are there? So there are typically four, right? So one combination is the actual class is predicted correctly. The second is, we have positive and negative classes. So the positive class is predicted as positive. The positive class, actual class is predicted as negative. So two combinations there. And negative class predicted as positive class, and negative class predicted as negative class. So there are four possibilities, right? So we'll look at the possibilities later, but a better way of doing this split, the better way of doing this training data set is to do something called as k-fold cross validation. So one disadvantage you can right away see from this slide is that we are using only part of the ground truth to train the model, right? So we are the validation data set, which is part of the ground truth, is never used for training. It is used only for validation or testing the model. So a better way of doing it is the k-fold cross validation. So in this, what we do is we split the data set, the ground truth, into a number of folds. So in this case, k folds, k parts. So just like before, one part will be used for validation and the remaining used for training the model. But the difference is we do k number of runs. We perform a series of k runs. And each of the k parts in turn is used as a test set or the validation set. And the other k minus 1 parts are used as a training set. So we do k runs, and each time we alternate or we change the validation data set. So first case, the first part, the second run, the second part, third run, the third part, and so on. So the total number of instances correctly classified in all the k runs is divided by the total number of instances to give an overall level of the predictive performance or predictive accuracy of the model. So the good part is that the k-fold cross-validation utilizes all the data for both training and validation. So therefore, the data utility is maximized. And the other good thing is it generalizes well, so it avoids overfitting because each time the training data set is different, right? So in that sense, um, it generalizes well. So that helps in deeper analysis of the model performance across different subsets of data. So we are also evaluating, we are training on different data sets in each run, and we are also validating on different data sets. So it's a more comprehensive evaluation of the model. So what we do is, I mean, this is again illustrating using a different kind of figure. So we we split the data set into k parts. Each by the number of rows in the first, in the original data set is m, we divide it into k parts. So we get m by k times n dimensionality matrices like this. And each time we change the validation data set or the test data set. It's called test data because we're testing the model, right? We are validating the model and testing the model. So that's why it's called as test data set. So each time we vary the test data set, and so we compute the accuracy as the accuracy in each of these runs, take the average of the accuracies in each of these runs. So that is the idea of k-fold cross-validation. So like we talked, there are four possibilities of binary classification. So true positive, and a simple example is, so this confusion matrix is not new. It has been in use for medical domain also. So let us take an example from the medical domain to illustrate the point. So when the actual class is positive and the predicted class is also positive, it's called true positive. So an example is a blood test correctly identifying a patient as diabetic, right? So that is a true positive case. Now, when the actual class is negative, that means the healthy person, the person is a healthy person, there's no diabetes, but the test incorrectly predicts that the patient is a diabetic. So that is called false positive, also called as type 1 error. So this is the type 1 error, where healthy people are incorrectly identified as diabetic. So that is not a good performance. Similarly, when a diabetic patient is incorrectly identified as healthy, it is called false negative. So actually the person is diabetic positive, but the test predicted as negative. So that is called type 2 error. And when the healthy people are correctly identified as healthy, then it's called true negative. The person is not a diabetic in reality, and the test also identified as not diabetic. So that's a true negative. So the goal of machine learning model should be to maximize the true positives and true negatives. So the prefix true means that the performance is good. The prefix false means that the performance is not good and the predictions are incorrect. So that's the way to think of it. So a question to you. Um, uh, which one? Okay, let me explain a scenario, then maybe I can ask the question. Uh, so in this example, from a paper published by Ian Goodfellow and others in 2014. So they trained the machine learning model on images of pandas. Um, and they could achieve an accuracy of 57.7% accuracy in predicting pandas. Um, then what they did is they added a noise. So nematode, is a worm. So by adding an imperceptible small amount of noise, Gaussian noise, the authors could trick GoogleNet. GoogleNet is the image classification model. So they tricked the model uh, to to make it predict images of pandas as gibbons. So originally, pandas were classified with 57.7% confidence accuracy. They added 0.007% of this kind of noise, Gaussian noise, uh, uh, to this image to produce this kind of an image. I mean, humanly, we hardly are able to distinguish between the panda on the left-hand side and the right-hand side. But GoogleNet got confused and it started predicting this image on the far right as a gibbon with 99.3% confidence. So that is the fallibility of machine learning models. So it's an adversarial attack on the machine learning model. Uh, so now the question is, what type of adversarial attack is this? Is it a type 1 attack or a type 2 attack? You can take some time to think, but in the interest of time, I will give away the answer. The answer is it's a type 2 adversarial attack. So if a panda cannot be identified as a panda, it's a false negative. And if a different animal is identified as panda, it's a false positive. So the related question is, which of these is more difficult to achieve? Type 1 error, a type 1 attack, or type 2 attack? So I'll give you more time to, okay, the answer, yeah, good, false positive. Somebody posted an answer there in the chat window. So the answer is type 2 attack is much easier. Now the next question is why? Why is type 2 attack much easier? The reason is because if you want to simulate a type 1 adversarial attack, then you must give a sample that the classifier thinks that it is a it's the same class, but the inputs are clearly distinct. That means if you give a gibbon on the left-hand side, you should trick the model to think that it is a panda. As you can see, that is a very difficult task, right? So that's the reason why type 1 attacks are slightly difficult. Uh, unlike type 2 adversarial attack, we need to drastically modify an input. So we need to modify the gibbon image to make the model believe that it's a panda, which is a difficult task. So, so that is the so that is that illustrates how important the distinction between type 1 and type 2 errors. Uh, So let us look at a few more metrics, right? We talked about accuracy, which is the number of correctly classified uh, proportion of the predictions, right? So true positives plus true negatives divided by the all the instances of the samples. So this confusion matrix is very important. So we'll keep encountering this confusion matrix on the top throughout the discussion. So, so accuracy is quite intuitive, no confusion about it. Uh, and then the total actual positives is given by TP plus Fn. So if you remember, the x-axis is the actual values and the y-axis is the predicted values. If you look at the confusion matrix, predicted is the y-axis, x-axis is the actual. So, so total actual positives is this column TP plus Fn. Similarly, the total actual negatives is Fp plus Tm. And then the another important metric for measuring the uh, performance of machine learning models is the sensitivity, or also called as recall. In the context of information retrieval, it can, or in the context of databases, it can be thought of as recall. How well the model or the search engine is, or the database search is in recalling the um, uh, right items. It's also called sensitivity. So the reason is it indicates how sensitive the algorithm is in finding true positives. So the more sensitive and subtle, the more it can find true positives. So for instance, diseases like cancer. So we want this test to be as sensitive as possible in detecting the true positives. It's okay even if we get some true false positives, but identifying the true positives is very important because missing some cancer patients is a dangerous thing. So that is the idea of sensitivity. We measure how sensitive the algorithm is in finding true positives. Another metric is called false positive rate. Um, so as the name indicates, it's the rate at which the false positives are produced by the model. So the numerator is the number of false positives and the denominator is the total number of instances or samples. So specificity is given by 1 minus the false positive rate. So specificity tells how liberal or specific the algorithm is. Um, so if there are many false positives, then the model is considered liberal, right? Like if a lot of students get A plus in a course, the instructor or the professor is considered liberal, whereas uh, only the most deserving students get an A plus, and the grading scheme is quite appropriate. Then we call the professor as more specific, right? So that's the difference between specificity and liberalness. So which one do you prefer? You want the professor to be liberal or specific? So that is something to think about. At least the industries want the professors to be as specific as possible because they trust the grades, right? If the credibility is lost in grading, then it's difficult. Yeah, so the answer, some answers in the chat window say specific. So thanks for those answers. Um, so specificity is that. And then there is something called precision. Precision is the true positive, the true positives divided by the true positives plus false positives. So the goal of precision is to minimize the false positives. Um, so a nice pictorial Venn diagram is given here. So this could get confusing. As we progress through the metrics, it could really get confusing. So we need to understand these metrics in as many different ways as possible. So one way is to um, uh, take the help of these kind of Venn diagrams, right? So precision is given by this and recall is given by this. So an easy way to remember. Uh, so now precision and recall play a complementary role, right? So if you look at the precision, precision focuses on minimizing the false positives. If you look at the uh, formulae for precision, the false positive rate is in the uh, denominator. So we want to maximize precision, we want to minimize the false positives. So the focus is on minimizing false positives in case of precision. Whereas in case of recall, the focus is on minimizing false negatives. So if you see recall, the denominator has these false negatives. So the focus is on minimizing false negatives. So in each domain, domains can be different. For instance, in case of medical domain, what do you think is more important, precision or recall? Right? So the answer is recall because we want the, yeah, thanks for that answer. Yes, the answer is recall, right? Because we want the system to be as good in predicting the true positives as possible. So we want to minimize the false negatives. So recall is more important for health domain. Similarly, for certain domains, precision is more important. So how precise the classifier or system is in detecting true positives is sometimes more important. So it all depends on the cost of false positive versus the cost of false negatives. So let us take an example to illustrate this further. Uh, so these days, mails are anyway cold. Back when Hotmail was invented, the mails were hot. But these days, when I get a mail, I typically tend to mark it as spam or things like that. The reason is because my email address is on all the research papers and people can easily get the email address and they keep sending all sorts of mails. So it's kind of cold. So that's the reason why I call this cold mail spam filtering. So cold mail is new and is working on a spam filtering machine learning model. This is the scenario. So Coldmail is receiving 1 million mails in a day and 10,000 of which are spam. Just a hypothetical situation. Then what is the accuracy? So the accuracy of the model that classifies every mail as genuine is 990,000 by 1 million, which is 99%, which is really good. But if you look at the true positives, so in this case, positive is a spam mail. If you look at the true positives, it is zero, right? Because every mail is predicted as genuine. So therefore, true positive, which is a numerator of precision and recall, will be equal to zero. So accuracy is completely useless in this case. So accuracy of a model. Now, in the second case, accuracy, let us look at the accuracy of a model which classifies every mail as spam. So therefore, the accuracy is 10,000 by 1 million, which is just 1%. But if you look at the precision, uh, the precision is 10,000 by 1 million, which is 1%. But recall, look at the recall, it is 100% because it is able to recall all the 10,000 spam mails. So therefore, it is 100%. So, uh, so as you can see, none of the accuracy, precision, or recall give the true picture in all scenarios. So this is particularly important when the data is highly imbalanced. For instance, diagnosing cancer. Most of the patients are healthy. Only a very, very few patients uh, are cancer patients. So the data set is highly imbalanced. There are many more number of healthy patients than the patients with cancer. So in such cases, we need more metrics, right? There are many instances where we need more metrics. So let us look at more metrics then. So one other measure is called the F measure or the F score, and typically it's also called as F1 score. And it is a harmonic mean of precision and recall. If you remember, harmonic mean is given by this formula. So it is basically 2 into this whole thing, precision times recall by precision plus recall. So that's the harmonic mean. So what is the problem with this metric? The problem with this metric is that it gives equal importance to precision and recall. That means the domain characteristics are ignored. Right? For instance, in health domain, for instance, recall is more important than precision. Right? So therefore, we need more metrics. So a better form of the F measure is by using a beta constant, a constant beta. By the way, F measure and these F beta scores are particularly important when the data set is imbalanced. So this beta, by tuning the beta, we can deal with the trade-off between precision and recall. So beta is like a coefficient. So it acts somewhat like a weight for this precision and recall. Because it is occurring in the denominator, values greater than 1 will contribute to the precision, the weight of the precision inversely to the overall F, right? So by the way, what is the range of F1 score? Precision times recall by precision plus recall. It is, the range is 0 to 1. So when F1 is 1, precision is equal to recall. And when F1 is closer to 1, um, the model is said to be performing well. So that is F1. What about so F1 is when beta is equal to 1. What if beta is equal to 0.5? Which metric is given more importance, precision or recall, when beta is equal to 0.5? So I'll give the answer. You can pause and think, but I'll give the answer. The answer is the weight is on precision. Therefore, when beta is equal to 0.5, the attention is more on minimizing false positives. And when beta is equal to 1, there is a perfect balance of weight between precision and recall. And when beta is equal to 2, F2 measure, will put more attention on minimizing false negatives. So the weight is on recall. So less weight on precision and more weight on recall when the value of beta is 2. So that is the idea of the F beta measure, right? But typically we use F1 more commonly. So you can compute all these metrics that we talked about in by using the confusion matrix. So here's an example. So if you look at the predicted classes and the actual classes, so 183 of them have been 183 of the actual class one instances have been predicted as class one, and then 663 of class two have been predicted as class two. So that means this is the blue ones are the good ones, and the orange ones are the undesirable predictions. So this is the confusion matrix, and as you can see, you can apply all the formulae that we discussed earlier, these ones, to compute the metrics. Now, there is another new metric called kappa. We did not talk about it yet. We'll talk about it in a later slide, but I just wanted to mention that the importance of confusion matrix. The confusion matrix gives quite a comprehensive picture. Uh, and More ways to analyze the confusion matrix are on this table. This is from the Wikipedia. Um, so there's something called prevalence, which is P by P plus N, PPV, which is TP by PP, positive predictions. And then there is uh, F1 score, um, and false malus index, which is like the geometric mean of the recall and precision. We'll talk about a few of these ones like Matthews correlation coefficient and informedness and things like that in a little more detail later. But I just wanted to tell you that there are many, many more metrics that you can derive from the confusion matrix. So informedness, true positive rate, false negative rate. So all these are metrics which I highly recommend that you use for evaluating the performance. Why? Because the more comprehensive the performance, the better insights you gain into the machine learning model performance, the better you can assess. Same thing with the student performance, right? The more metrics that you use to evaluate the student performance, the more assignments, the more ways you use to evaluate the performance, the better it is. So now an interesting way of measuring performance is by varying the threshold, prediction threshold. So here's an example of tweets, right? So there are a bunch of tweets. Um, and some of these tweets are false and some of these tweets are true, right? So the machine learning, the red ones are false and the empty ones are true. Um, so machine learning model generates this kind of decision boundary between the true tweets and the false tweets. And how is this decision boundary generated? By using a model, a classifier, which is in the shape of S here. So by using this classifier on the y-axis, we generate the decision boundary. So in this case, as you can see, if this whole thing, the classifier range is from 0 to 1, 0 being this point and 1 being here, I mean on the y-axis. So the decision boundary was obtained by dividing the probability at 0.5. So from 0 to 0.5, the prediction probability is classified as false tweet, and 0.5 to 1, the prediction probability uh, classification is true tweet, right? So that's a simple way, a simple algorithm. So I usually take this example for my logistic regression class. So this model classifier is basically obtained by using an algorithm called logistic regression. And this function, which is in the shape of S, is basically the logistic function. So based on the output from the logistic function, we interpret it as a probability. The output from the logistic is interpreted as a probability. And based on the probability, we come up with the decision boundary. And typically 0.5 is the is is a reasonable way to come up with this decision boundary, because we can think that 50% are false and 50% are true. But let us look at a hypothetical situation where we move the threshold from 1 to 0. I mean, this should go even further down, but I'm just giving an example. So we move the threshold. So what happens when we move the threshold? Suppose this threshold is less than 0. What happens? Then this red line, the decision boundary, is below all the tweets. So then what does it mean? It means that all these tweets will be classified as true, right? Because all the lines above the decision boundary were true, and all the tweets below the line are false, right? So when the threshold is moved to below the minimum range, which is 0, then all the tweets are predicted as true. On the other hand, when the uh, the threshold is more than the maximum, that is more than 1, then all the tweets will be below the decision boundary, so all the tweets will be predicted as false. So let us look at this hypothetical situation algebraically. So when the threshold is more than the maximum of the classifier function, in this case, logistic regression, like I mentioned, that S-shaped function is called the logistic function. So when the threshold is more than that, so as you can see here, all the tweets are predicted as 0, right? True is 0 and uh, false is 1 in this case. So all cases, so this is the confusion matrix, right? The matrix on the left-hand side is the confusion matrix. So all cases are predicted as false, and the total number of predictions are B plus D, I mean, B plus D, which is the total. And the accuracy is a percentage of false tweets, which is percentage of zeros. So the accuracy is not 0. You have to keep that in mind. What is the accuracy here? Can somebody think and tell me? So the accuracy is this one, predicted correctly, right? 0 plus D by B plus D, right? So that is the accuracy. It's not 0. So you must keep that in mind. Now, when the threshold is less than the minimum of the function, possible values of the function, which is 0, all the cases are predicted true. So in this case, um, think that the true positives are A and the false negatives are C. So A plus C is the total. So the accuracy is the percentage predictions as true, which is A by A plus C. So once again, the accuracy is not 0. Just because you are doing something totally ridiculous by moving the threshold to greater than 1 or less than 0 does not mean that the accuracy will become 0. So there is still some accuracy. So this is a very important concept in measuring the performance of a model. First reason for this is uh, to uh, to to identify which threshold is optimum, right? Like in this case, we randomly decided that, I mean, not randomly, but intuitively, we thought that 0.5 would be a better threshold. But what if 0.7 was a better threshold or 0.3 was a better threshold? So how do we determine that threshold? Is by drawing what is called as a receiver operator characteristic um, curve, which we'll talk about a little later. But before that, let us look at what is called, let us look at this plot of accuracy versus the classification threshold. So for various thresholds, you plot the accuracy on the y-axis. The threshold is on the x-axis and the accuracy is on the y-axis. So in this case, we obtain this kind of a plot, and at we notice that at 0.7, the accuracy is maximum. At 0.7 threshold, the accuracy is 0.715. So as an aside, the true positive rate is 0.73 and the true negative rate is 0.7. I mean, these are just two metrics, just to give you an idea of the model performance. But the main idea I wanted to illustrate through this slide is that the way we choose the optimal threshold is by um, looking at the uh, threshold for which the accuracy is maximum. So that's the threshold which is typically chosen. So in this case, we are going to choose the threshold 0.7. So apparently the idea of changing the threshold was meaningless, but you see how powerful the idea is. Another plot that we typically use for measuring the performance is called the precision recall curve. So what we do is we plot the recall on the x-axis and the precision on the y-axis. And then we draw this y is equal to x line. So this is the break-even point where recall is equal to precision. Remember, there is always precision and recall are complementary. We talked about it here, right? They play a complementary role, complementary roles. Um, so, so we want both of them to be as good as possible. So the break-even point in this case is obtained at 0.68. So the more the points are towards this vertex, 1, 1 vertex, the better it is. We want the both recall and precision to be as high as possible, but that is not always possible, right? So that's the reason why we look at the break-even point. So the average precision in this case is given by 0.75. So this is another way to choose the threshold, right? Now comes the more important curve called the receiver operating characteristic curve. So this was developed in, I mean, you might be wondering why the name. The name is because it was developed in the World War II times to model false positive rate and the false negative detections of radar operations. So each point on this curve, the receiver operating characteristic curve, represents a different trade-off between false positives and false negatives or true positives. So it's like the cost benefit ratio. So, so for we again change the threshold values from 0 to 1. And oh, there is a something question on the, okay, so there are some questions on the chat window. Yeah, so is this same as the AUC? That's a good question. So the average precision, I think that refers to the average precision. Yes, that is right. So the average precision can be thought of as the area under the precision recall curve. So is this the same as finding? Yeah, the same thing. Yeah, same question. Right. So good thinking. This can be thought, the average precision can be thought of as the area under the curve, precision recall curve. But we'll talk about more in the context of ROC, the same concept of area under the curve. So once again, we vary the thresholds from 0 to 1, in this case 0.05 to 0.95. And we measure the true positive rate and the false positive rate for each of these thresholds. Uh, then we obtain this kind of for this data set, this is the plot on the left-hand side. So the x-axis is the false positive rate and the y-axis is the true positive rate. And we plot all the points for various thresholds. So that is the idea of a receiver operating characteristic curve. So slope of the line tangent to the curve defines the cost ratio. So what is the cost ratio here? So yeah, this indicates the curve indicates the model performance for various thresholds. And essentially, it's the cost benefit analysis of the model. So cost is the false positive rate and the benefit is the true positive rate. We want the true positive rate to weigh in more than the false positive rate. Um, so the slope of the line tangent at any point determines this cost ratio. So this metric has better statistical foundations than most other measures. In fact, it is used in biology and medicine also. Um, so what is the best point in this plot on the left-hand side? So think about it. I'll give you the answer in the next slide or next a few slides later. Um, and related to the question asked by someone in the audience, what does the area under the ROC curve represent? Any guesses? The area under the ROC curve represents the performance averaged across all possible cost ratios. So it gives a comprehensive metric of the performance of the machine learning model. So the area under the curve typically is between 0.5 and 1, and typically closer to 1 if the model is acceptable. So in most research papers, the area under the curve is synonymously used as accuracy, but both are different. So that is something to keep in mind. But if you look at most of the even highly cited research papers, they use AUCI for accuracy, but technically they are two different things. So another question, how does the ROC curve of a completely confused, totally random guessing classifier look like? And what is its AUC, area under the curve? So that is this dotted line, right? So the dotted line represents a confused model, totally confused model, and the area under the curve is 0.5. So it's unable to decide whether the class is a positive class or a negative class correctly most of the time. It's like a coin toss. It's completely confused. So that is the idea. So for this curve, this green curve, the area under the curve is 0.782, which is reasonably good. The accuracy, it roughly corresponds to the accuracy of the model. So it's like 0.782. So if the area under the curve is 1, then it is perfect prediction. If it is 0.5, it is random prediction. And if it is less than 0.5, then something is wrong. So you need to either change the model, change the algorithm, or change the hyperparameters and things like that. So this dotted line is a random guess. If the model is simply guessing the classes at random, that's what happens. So there's a question, how does AUC relate to MAP 0.5 and MAP 0.5 to 0.95? So we'll cover that a little later. I'm kind of running late on, I don't want to introduce a new concept at this stage. Um, uh, so let us look at the properties of the ideal ROC curve. So the points 0, 0, and 1, 1 are on the ROC curve. Of an ideal ROC curve. These are the properties of ideal ROC curve. So this is from a paper uh, by Hart and others. So you can look at this paper for the proofs if you are interested. And RSC curve typically lies above the main diagonal. The x is equal to y diagonal. RSC curve must typically lie above the main line. Otherwise, there's something seriously wrong with the model. And the RSC curve is typically concave. So these are some of the properties of ideal ROC curve. But what if there are multiple models and these multiple models are intersecting, right? So in this case, the purple model is model A. This purple line is model A. It performs better than model B, the green line. For some, I mean, in general, it performs well. Um, and so the green model is performing slightly less uh, better than the purple model, and the orange model is not performing as good as model A and model B. Um, so so as you can see, the area under the curves are listed here. Model A is performing better. So another way to think of it is if two ROC curves are intersecting, it implies that one method is better for some cost ratios and the other method is better for other cost ratios. So for instance, green is better for certain cost ratios, certain thresholds. And then purple picks up from there on, and it performs better for the remaining cost thresholds. Um, Same with orange and green. And if the two ROC curves do not intersect, what does it mean? It means that one method dominates the other for all possible thresholds. So it's the unconditionally superlative. So that's what it means. So that is the interpretation. Um, so let us look at the various models on an RSC plot. Models A, B, C, and D for some threshold. So let us look at some of these points. So what can you tell about this point? What can you tell about the model performance of this point? Good, bad, poor, average, conservative, liberal. What can you tell about it? It's excellent. That's right. The answer is it's excellent. Thanks for that answer. Yes, it is good. How about this point? What can you tell about this? Is it good, bad, liberal, conservative? Let's look at the answers. So ideally, you want to get as close to the top left corner as possible. So one answer is random confused. I don't think so. It is close to that, but um, this is more liberal, right? This point is more liberal. The model is more liberal. Why? Because there are a lot of false positives, but at the same time, there are a lot of true positives also. So it is more liberal. It's like the professor who gives A and A plus to most of the students. So there are a lot of true positives because most of the students in the class are typically good, right? Otherwise, they would not have passed through the entrance exams and all that stuff. They would not have been selected for the program. So, but only thing is there are a lot of false positives also because the professor is liberal. So that is the idea of a liberal model as well. A lot of true positives and at the same time, a lot of false positives. How about this point? I think the answer is already there. Somebody gave the answer on the chat window. It is the best possible option. So the model is here. It's perfect model. 0, 1. And how about this? What can you tell about that? So in this case, true positive rate is equal to false positive rate. So it is like a liberal model as well. And how about this? What can you tell about this? Uh, okay, the one question is, isn't it more random than liberal since it is good at guessing? Um, so randomness implies that it would get the true positives also randomly. That is not happening, right? Um, uh, if the point is on this dotted line, then it is random. You can think of it as random, but the point is also has some good false true positive rate. So if the professor is totally random in giving grades, then there will be a lot of people failing the exam also, right? But here there are some good true positives also. That's why the point B is liberal, can be considered liberal rather than random. Good question. So this point here, how do you classify it? Is it good, bad, conservative, uh, or poor? I'll give the answer. The answer is conservative. Why is it conservative? Because it is making sure that the students get the right grades and making sure that no student gets an A plus by chance, right? So that is a conservative behavior, very conservative behavior. True positives, it is able to identify, but it is to identify more true positives, it's a bit conservative. It's not sure whether it could be a false positive. So that's why it's it's conservative. Uh, yeah, it's not great. Yes, that is a message on the chat window. And how about this one? This point here at the bottom left. It's obviously a poor performing model, right? Because it is not yielding a lot of true positives and it is yielding a lot of false positives. So it is poor. How about this one? This point on the x is equal to y line is a random guess. So model is behaving randomly, totally randomly. Yeah, so the answers are all correct on the chat window. Good. Okay, now let us talk about a related concept, which is the Cohen's kappa statistic, or Cohen's constant, kappa constant. Um, so this is a very interesting idea. So the kappa statistic measures the agreement between the evaluations of actual and predicted values. So basically, it tries to answer this question. Do you agree with the evaluation metrics? I mean, we have completed all these nice evaluation metrics, recall, precision, and accuracy, and F1 score, and all that. But do you really agree with these evaluation metrics? So similar to the question, this student got an A plus. Do you agree with the evaluation, whether the student got an A plus, that the student got an A plus? So this is particularly useful when dealing with imbalanced data. So that means one class dominates the other class. So it's somewhat like the p-value. But anyway, I don't want to introduce the new concepts. So it describes the agreement achieved beyond chance as a proportion of that agreement which is possible beyond chance. So the idea is chance here. So here's an example, right? So take a system which keeps flipping coins. So a set of biased coins turns heads 90% of the time. What is the best accuracy of a random system used for prediction? Suppose random system is there. So what is the best accuracy it can achieve? So I'll also give a hint. The best case is when always the model always predicts a majority class. So here's an example, right? Suppose the exams were all super easy and everyone got an A grade. So then the A grade is attributable to chance rather than to the student, right? Um, suppose the student already had the questions leaked out. He would anyway get an A. So we need a way to test for fairness also. So that's what kappa statistic does, right? Um, so, uh, so suppose a student is totally unprepared for the exam. It's a multiple choice question, true or false question, questions. All are true or false questions, and the student is totally unprepared for the exam. So, what is the best accuracy that the student can obtain? Um, one typically what students would, smart student used to do when I was a high school student is the student would choose true for all the questions. The answer is true for all the questions. Then by if the instructor, the professor is more optimistic, then the answers would be anyway true. So so he would, if 90% of the time the answers are true, this student would get a 90% score on the exam, right? So the best accuracy of a random system used for prediction when the original paper is biased, original question paper is biased, or original data set is biased, with 90% of one class and 10% of the other class is 90%, right? Let's see. Okay. And if the accuracy of a system that you designed is also 90%, suppose this student got 90% in the exam, how much of that accuracy is attributable to chance? So we know that a student who marks true for all the answers gets 90% by chance, and one student got 90%. So what is the uh, possibility that the entire accuracy is attributable to chance? It is 100%, right? It is quite possible that the student might have just guessed true for all the answers and got 90%. So that is the idea of kappa coefficient or uh, kappa constant, kappa statistic. So it is the agreement beyond chance, and in this case, it is equal to 0. So the student got a 90% on the exam, but we cannot trust it because the agreement beyond chance is 0. So the design system modeled the bias in the coin and could not overcome the bias. That's another way to interpret the kappa coefficient. So it simply modeled the bias in the coin. The question paper was biased towards true answers, and therefore, uh, the if somebody gets 90%, then it's likely that the person cheated or guessed randomly. So typically, the kappa statistic ranges from 0 to 1, but you could also get negative kappa score. So a value of 1 indicates perfect agreement. A value of 0 indicates that agreement is no better than chance. And a negative kappa coefficient indicates that the agreement is worse than expected or pretty much disagreement. So generally for machine learning models, a kappa score of more than 0.4 is considered satisfactory. Um, So low negative values of kappa score may be considered as no agreement. I mean, they're close to 0, so no agreement. But if the negative value is high, like minus something, minus 0.5 or something, then it represents great disagreement kind of thing. So that's how you interpret the Cohen's kappa score. So the formula for calculating the kappa statistics is easy. It's PO minus PE divided by 1 minus PE. But what is PO and what is PE? PO is the proportion of observed agreements, and PE is the proportion of agreements expected by chance. So agreements, you can think of them as matches. So predicted class and the actual class are matching. Then it's called an agreement. So in that sense, PO can be thought of as accuracy, right? And we subtract the chance factor from it to determine the kappa score. Let us look at it in a more intuitive way. So kappa score is given by 1 minus. So a very perfect model will have a kappa score of 1, but you need to subtract the portion due to chance. So the portion due to chance is given by this. 1 minus accuracy divided by 1 minus accuracy due to chance. So which is equal to accuracy minus accuracy due to chance divided by 1 minus accuracy due to chance. So that is the idea. So we are removing the chance factor from the accuracy. So how do we compute the PE? PE is a probability of occurrence of two disjoint events. So what are the two disjoint events? So pause to think, but I'll give the answer anyway. So the two disjoint events are predicting positive by chance. So remember, we are still in this binary classification. So two classes, one class we choose to call it positive, second class we call it negative. So PE is a probability of the two events predicting positive by chance and predicting negative by chance. So these are the two disjoint events. And what is the probability for predicting positive by chance? So the probability can be determined by considering the event in detail. And for predicting positive by chance, two events must happen. What are the two events? Pause to think. For each of the question, pause to think, but I'll give the answer in the interest of time. So the prediction must be positive for the instance, and the actual class must be positive, like the coin bias, right? Like in the case of the coin bias. So remember, all these events are assumed to be independent. So we are not assuming any dependence. We are not considering any dependence among the events. So all these events are independent of each other. So therefore, we can obtain the probabilities by simply multiplying. So in case of predicting positive by chance, it's a multiplication of the probability of positive prediction times the probability of actual class being positive. And how do you find these probabilities? From the confusion matrix again, right? So for instance, so in this case of this confusion matrix, the kappa statistics is given by this formula, 2 times AD minus BC by P1 Q2 plus P2 Q1. But how did we get this? By computing the probabilities. So PO is basically the accuracy, which is observed matches, which is A plus D. Remember, true positive and true negative. So A plus D by the all the instances. So that is accuracy. PO is easy to compute. The problem is only with PE. So P, and that also is quite simple based on the intuition. So for P positive, positive class, we assume independence, of course, and multiply two probabilities. What are the two probabilities? The two probabilities are probability of positive prediction and probability of actual class being positive. What is the probability of true prediction? It is A plus B. Prediction plus is A plus B by the whole number of instances. And similarly, the other probability is A plus C by A plus B plus C plus D. Similarly, P minus will be B plus D, which is uh, actual negative, the probability of actual negative, and the predicted negative, the probability of predicted negative. So you sum them up, you substitute and simplify, you get this formula. You get this formula, 2 times AD minus BC by P1 Q2 plus P2 Q1. So why are we doing all this? Let us take an example. So here's an example. So in the actual data set, you have 44 um, uh, plus, 50 positive classes and 50 negative classes distributed in this confusion matrix. So the kappa score is given by that formula, 2 times whatever, AD minus BC and all that stuff. So when we compute the kappa score, it is 0.8. And when you compute the accuracy, it is 0.9. So 44 plus 46 by 100, which is 0.9. So which is good. 0.8 is a reasonably, is a decent score for kappa score. So we can trust the accuracy here in this case. But look at this. Yeah, K is equal to this one. But look at this. Here, The accuracy is still 0.9 because 84 plus 6 divided by 100 is 0.9. But if you look at the kappa score, it is 0.12. If you substitute A, D, P1, Q1 and all that in this formula, then you get 0.12. So that means there is very little agreement. Most of the agreement is by chance, right? So we cannot trust this accuracy anymore. That's what it means. So with imbalanced data set, the problem here is, what is the problem here with the data set? The problem is imbalanced data set. Because in the previous case, the data set was perfectly balanced. The actual class was 50 plus, 50 minus, but in this case, the actual class 90 plus and 10 minus. So that is the problem. That is why we ran into this problem. So Cohen's kappa score is able to detect such imbalances in the data set and such problems in the accuracies. So accuracy cannot be trusted entirely. So that is the takeaway from this slide. So let us talk a little bit about balanced versus imbalanced data set. So in the world, most of the data sets are balanced. For instance, gender ratio, in spite of some attempts to manipulate it by God's creation, God's magic or the creativity, the gender ratio is continuing to be holding strong, right? That is the power of nature. So most, like gender ratio, most of the data sets are balanced. We don't have to worry about imbalanced data sets. But there are a few data sets where the data set could be highly imbalanced, right? Like in the case of credit card fraud. Very few transactions are fraudulent. Most of the transactions are genuine, right? For various reasons. I'm not going to the social aspects of it, but so that is the idea. So the algorithm in this kind of imbalanced data sets is prone to overfitting the majority class. By default, it tries to predict genuine, right? Just like the student, right? In the midterm, most of the answers were true instead of false. So that intuition is carried forward, and the student tries to predict truth in the final exam also, right? So just like the student, the algorithm is also prone to overfitting the majority class. So just by predicting the majority class, models could score high on accuracy on their loss functions, right? So that is the problem. So how do you correct this problem? How do we correct this kind of a data set which is imbalanced? So there are two ways. One way is to reduce this blue area to match the orange area, which is called undersampling, right? In undersampling, what we do is, so the original data set is like this. Green is one class, blue is the other class. So we undersample the majority class by randomly choosing only that many number of samples which equal the minority class. But what is the problem with that? The problem is we are losing data. Machine learning models are very hungry for data. So if you give it less data, then they'll perform poorly. So that's the reason why undersampling is not often used. Instead, oversampling is used. So oversampling, so in undersampling, we randomly select observations. So you are eliminating some tuples from the majority class. But in oversampling, we create minority class samples synthetically. So that is the interesting part. We are going to create these minority samples synthetically, means artificially. But statisticians do not necessarily agree with this idea because statistically oversampling is not desired. So it is not typically used in statistics, but it is heavily used in machine learning. In fact, generative AI is being used increasingly for creating synthetic machine learning samples, data sets, right? So how do we do this? A very simple idea was proposed by this paper by Chawla and others. This technique is called synthetic minority oversampling technique. Um, so the idea is to add synthetic tuples, like I mentioned, but these tuples are same as samples, instances, rows. All these mean the same. Um, so, so, so each of the data points or the tuples are these points in this vector space. So what we are going to do is we are going to add some synthetic data points or rows in the table data set that are close to a given minority class sample in the vector space. So for each minority data item, so in this case, the minority class is green and the majority class is blue. And these pink data points are the synthetic samples we are going to create using this algorithm called SMOTE. Um, so for each, so the algorithm is very simple. For each minority class or minority instance, minority data point, k nearest neighbors belonging to the same class are determined. So you take this, say, for you take this green point in the center here. We determine k number of neighbors. So this one, this one, this one, this one, this one. All the k nearest neighbors are determined. Then a fraction of them are chosen randomly. For instance, we choose this, but not this, randomly. And this is nearer to this point than this. But we chose this point because the choice should be random to eliminate any bias. So we randomly choose a few points like that, a fraction of them. And for each sample, um, we choose a neighbor. So we choose a neighbor and draw a line connecting the two samples. So in this case, so this is the original point, and we choose this point and we connect them, right? And then a synthetic data item, a synthetic sample is generated randomly on the line connecting the 2 points. So this example neighbor pair, this is the example and this is the neighbor, this is the pair. So on the line connecting the 2 points, we generate a synthetic sample randomly. Again, to avoid bias, we make it random. Right. So the exact position of the example is uniformly random along the line segment. So this synthetic example is added to the data set now. So that is called as oversampling. So all these pink points, which are generated randomly, are added to the data set to make the classes balanced like this. Right. So each of these green boxes are randomly generated using this kind of an algorithm. But there's a small problem with this, right? Or an improvement over this is what is called as adaptive synthetic sampling. So in this case, we focus on a section of the points. In this case, in the previous case, we did not, we considered all the minority class samples as similar, but in the case of adaptive sampling, we prioritize certain points in the minority class. Any guesses on what points we are going to focus on? What points, what minority class points are we going to focus on? So you can pause to think. I'll give the answer in a while, but so the idea is first is to do some homework. The homework is to first calculate the degree of class imbalance. How imbalanced is the data set? How do you calculate the imbalance? Simply by taking the ratio. So M small divided by M large. So number of samples in the minority class divided by the number of samples in the majority class. That's the ratio. And so you determine a threshold, and while the threshold, while D the class imbalance is less than threshold, so the goal is to balance the data set, right? So we come up with a threshold. So the threshold could be 1. Ideally, it could be 1. That means you are completely balanced the data set. But that is not always desirable, right? Because creating too many synthetic samples can lead to overfitting, right? Especially if the model learns the noise in the generated data. So there are some disadvantages to doing oversampling. That is the reason why statisticians are not in favor of that. So we typically do not set this to 1, right? So until this threshold ratio is met, we keep calculating the number of synthetic data samples that need to be generated for the minority class. So G is uh, the number of samples that need to be generated. So which is given by the difference between the majority class and the minority class, number of majority class items and the number of minority class items multiplied by beta, which is the ratio. So how do you identify the minority class samples that are difficult to classify? So the focus is on the minority class samples, which are difficult to classify because the performance of an algorithm is determined by how well. See, see, grading the best performing student as A plus and the worst performing student as C or B minus or something like that is not too difficult a task. But those border cases, like the students who are between they're doing well and not doing well. So those kind of cases matter the most, right? Same with so there's anyway. I don't want to introduce new concepts. So that is the idea. We want to focus on the samples which are difficult to classify. So that's where the model's behavior is more accurately determined, right? So how do you identify such samples? So what are the common characteristics of such samples? You will find that they are closest to the decision boundary in the region of disagreement. So these points are closer to the decision boundary and they are surrounded by samples of majority class. So if you look at this, the treats example that we saw here, so the difficult treats are these ones, this one and this one, which are closer to the decision boundary. Any model will be able to, any reasonably performing model will be able to classify these points reasonably, the extreme false and extreme true. But the problem comes only with these points which are in the region of disagreement. This region is called region of disagreement because many models disagree on whether to classify this as true or false, whether to classify this as false or true, right? So that's where the performance of the model is determined. So we want to focus on points near the decision boundary. And as you can see, these points are surrounded by the other class points, right? So for instance, this point is surrounded by, if you look at this, these points are as close as this point. So the minority class, I mean, the other class samples are close to this compared to this. For instance, you take this, most of the surrounding points are true. Whereas for this, quite a few of the surrounding points are false. So we want to focus on these points, which have the other class points in the neighborhood, surrounded by samples of the majority class. So ADASYN, this algorithm called ADASYN, factors this into the choice of minority class points. So that's the key idea. The rest of the algorithm is pretty much similar to what we talked in SMOTE, but this is the key idea that differentiates the Addison algorithm. So it works by identifying the minority class samples that are difficult to classify. So that's the idea. So for each, so how do we identify such samples? Um, uh, how do you identify the borderline samples? So first, we for each sample x in the xi in the minority class. So these are SMOTE. This algorithm is this part of the algorithm is very similar to the SMOTE algorithm we talked earlier. So we find k nearest neighbors based on the Euclidean distance in n-dimensional space and calculate the ratio Ri defined as delta I by k, where delta I is the number of examples in the k nearest neighbors of xi that belong to the majority class, not minority class, but majority class. So that's how we check for the neighborhood of each point. We are making sure that the neighborhood comprises of majority class points, the different class. So that's one indication of decision boundary. And then we normalize. So we're not yet in the SMOTE type of algorithm. We are still in the Addison part, adaptive synthesis. So then we normalize this Ri, right? So normalization, normalization is a typically used factor. So we normalize according by, you know the idea of normalizing. It should all sum up to 1. So that's the reason why we compute this density distribution, right? So that it all sums up to 1. So that is, so once we have this stuff, the rest of the algorithm is pretty much similar to the SMOTE example, SMOTE algorithm. So we calculate the number of synthetic data examples that need to be generated for each minority example, right? So for each example, each instance of the data, how many synthetic samples must be generated is what is computed here. So remember in the SMOTE, what did we do? So for this point, we generated how many synthetic samples? 1, 2, 3, 4, 5 synthetic samples. So that's what we are doing here. GI is the 5 synthetic samples I showed on the previous slide. So we compute the number of samples that need to be generated by using this simple arithmetic, which is the total number of synthetic data samples that need to be generated. And for each minority class example, generate GI synthetic data examples according to the following steps. So this is again very similar to the SMOTE algorithm. So xi is the example point and xji is the neighborhood. We determine a point on the line connecting xi and xji randomly by choosing lambda, right? So this is xi in the center and xgi is this point. We randomly choose this point here on the line connecting the two, which is given by lambda, right? In this case, the authors of the research paper call it lambda. And the rest of the algorithm is pretty similar to SMOTE. So that is the idea of adaptive synthetic sample. So there are many such, there are multiple such algorithms. I don't want to cover all those algorithms. But the point I want to make is, so in this research paper that won the best paper award in 2023 IEEE conference, IEEE sponsored conference, we stated that the experiments also demonstrate that some of the oversampling techniques can actually degrade the models both in terms of performance and fairness. So that was a conclusion that uh, we drew about the oversampling techniques like Addison, SMOTE, and all. So why is that the reason? The reason is, like I mentioned, when synthetic samples are generated, they are based on existing minority class data items. So this can lead to the classifier learning the patterns which are specific to the training data, but do not generalize well to the new unseen data. Right? You get the point? We are basing the new points on the existing training data set. That means we are kind of overfitting to the training data set. Right? The synthetic points are based on the existing training data set. So that's why there is some amount of overfitting. So that, and overfitting will degrade the performance and also the fairness aspects. And another reason is uh, these are all synthetic samples, so they may not accurately represent the true distribution of the minority class. In reality, the minority classes may be somewhat distributed differently. So that is the other reason. And the third reason is that some synthetic samples may be generated in regions um, that actually belong to the majority class, right? If the decision boundary is very subtle, right? If it is very subtle, then it is likely that the region actually belongs to the majority class. And because we are drawing a line and thinking that the entire space between the two minority class points is also minority class, it may not really be the case. So oversampling kind of is oversimplifying the real world relationships. Real world relationships can be much more complex. So that's another reason for poor performance. So we computed F1 score, we computed accuracy, we computed a lot of metrics, and we determined that the algorithms actually do not perform all that well. So as you can see, when none of these oversampling techniques are used, the performance is much better than when these methods are used. So clearly not all oversampling techniques address the fairness issues. So the measure for fairness is basically F1 score and Cohen's score, right? Cohen's kappa statistics. In both cases, we notice that oversampling techniques actually do not, in some cases at least, they did not perform well. So that means there is a lot of scope for research in this area. So that's the point I wanted to make. And I also wanted to demonstrate the importance of F1 score and Cohen's kappa score. And also to show that Cohen's kappa score does it better than F1. So for more details, try to read this paper. It's on Google Scholar and IEEE Explore. So there are several other classification metrics. For instance, G measured is a geometric mean of precision and recall. It has a fancy name, which we talked earlier also. Then there is something called informedness, which was also covered in one of the earlier slides briefly. So informedness or Uden's J statistics or Uden's index, as it is called, is the sum of sensitivity and specificity minus one. By the way, what is the best value of sensitivity and what is the best value of specificity? Both are one, right? Best sensitivity value is one, best specificity value is also one. So which one do you want? Which one do you prefer, specificity or liberal? So take the instance of governments, right? I'm giving a lot of examples from my academia, but let us look at governments. We want the governments to be sensitive and specific, right? We don't want the governments to be insensitive and liberal, right? Same with machine learning models. We want the models to be sensitive and specific as much as possible. So informedness will tell you that, will give you that representation. So a value of 1 indicates perfect classification performance. 0 means no better than random chance. A value below 0 indicates that the model performance is worse than random chance. Another metric is markedness, which is the PPV plus NPV minus 1, which we saw in the earlier slides. positive predictive value, PPV, is given by TP by TP plus FP, and negative predicted value is this. And then Matthews correlation coefficient, MCC, combines informedness and markedness together. So that's the power of MCC. In fact, these days, MCC is being more used than accuracy in machine learning. So MCC is given by this formula. Um, so the range of MCC is -1 for perfect misclassification and +1 for perfect classification. And can you tell me when this formula doesn't work? It doesn't work when the whole row or column of a confusion matrix is 0. So when true positive is equal to false positive is equal to 0, or when true negative is equal to false negative is equal to 0, then it does not, it is undefined, right? So when is it 0? When is the Matthews correlation coefficient 0? When the numerator is 0. So for perfect random prediction, like a coin tossing classifier, the Matthews correlation coefficient is equal to 0. That means TP times Tn is equal to FP times Fn. And when is it 1? It is 1 when the classification is perfect. When is the classification perfect? The classification is perfect when there are no false positives and when there are no false negatives. Fp is equal to Fn is equal to 0. And when is it -1? When all the predictions are incorrect. That means true positive is equal to true negative is equal to 0, right? So that is the idea of, see, it encompasses so many border cases. So that's the reason why MCC is a balanced measure. It's quite comprehensive, includes all 4 elements of the confusion matrix, and it is often preferred over F1 score. Even for imbalanced data set, MCC is preferred to accuracy. So this is a nice nice depiction that I got from this website of the various performance metrics on imbalanced data. So if you look at this, so you vary the threshold, and then you compute the true negatives, false positives, false negatives, and all that. And the red, on the left-hand side, the red-brown mountain, reddish-brown mountain, to the left is a majority class. Right? And so the confusion matrix is kind of indicated in this plot here on the left-hand side. So this is the output probability, and x-axis is the output probability, y-axis is the frequency of the occurrence. And so this mountain is kind of indicating the majority class. And as you can see, accuracy, which is the purple line, is still high on the right side, but not MCC and F1 score. So MCC is this green one. So I know the color is a bit confusing, but if you see, accuracy is keeping on going up with the increase in threshold, but other metrics are going down, right? So that is the reason why accuracy alone is not sufficient to model the performance of machine learning models. So a few papers which cite MCC. So in one paper by Chico and others published in 2023, they claim that we explain why MCC should replace the ROC AUC, area under the receiver operating characteristic curve, as standard statistic in all the scientific studies involving a binary classification in all scientific fields. That's a very dramatic statement, in my opinion. So they are recommending MCC to replace the accuracy metrics that have been conventionally used. So this is what they claim in a quite a reputed paper. I mean, this is indexed by the government website, National Institute of Health. So that means it's pretty good. And let me see, where is this published? Biodata mining. So I think it's a good journal as well. So that's what they claim. But again, there are some contradictory claims as well. Like in 2020, Zoo and others say that it has been generally regarded as a balance measure which can be used and all that stuff, so which we already know. But they claim that the study of this paper finds that this is not true. MCC deteriorates seriously when the data set in classification is imbalanced. So again, you have to use some discretion when using these metrics. So no single metric, in my opinion. This kind of blanket statements, I'm not very much in favor. I would recommend more comprehensive evaluation of the machine learning models. Do not depend on any single metric. So having said that, there are many other metrics. So one other such metric is called the lift. So lift is the sensitivity of the model by the ratio of the actual positives. If you look at the confusion matrix. And so it is kind of indicating the ratio between the results obtained with and without the predictive model. So when you use a machine learning model, this is the blue line is what you get. And when you don't use a machine learning model, it is as good as random guess and you get this red line, right? So y-axis is the true positive rate and the x-axis is the sample size. Now, the good thing about this plot is that you will be also be able to determine what sample size is good enough for us. So for instance, if we consider just 80% is good enough for our domain, then you can work with just 50% of the sample, right? Because data is expensive, typically. So for training the model, you can just use 50% of the sample and then still get a validation accuracy of 80%, right? So this is one good use of lift, the metric lift. So it kind of helps us determine by how much we can skim the data set by selecting a relatively small number of instances and getting a very good accuracy metrics rather, performance metrics. So the greater the area between the lift curve and the baseline is this red one without the model, the better it is, right? Once again, the closer the model is, the lift chart is towards the top left, the better it is. Let me check. Okay. So now moving on to regression metrics. Uh, So machine learning is typically used for two primary reasons. One is classification and the other is regression. Regression is when we predict a continuous value. In classification, we predict a discrete variable, which can take only a few limited set of values. For instance, in binary classification, the target variable can take only two classes, positive and negative, typically. Could be anything else, true or false, and good or bad, and all sorts of things. Or in some cases, it could take multiple discrete classes. Like in case of students, it could take the grade, like A plus, A minus, A, B plus, B minus. All those are discrete classes. So that is classification. But regression, on the other hand, predicts a continuous values. What is the continuous value? Income, scores in a subject, what is age, so on and so forth. So that's the, okay, let me see yeah, quantitative values. That's right. So some of the metrics to measure the performance of regression models is the first thing is the mean absolute error, MAE, given by the predicted value, which is typically denoted by this hat symbol, and the actual value, which is yj here. So we don't care whether it is this way or that way. So that's the reason why we take the absolute value, modulus operator, um, modulo, and then we average this difference between the predicted and actual values. So that gives you the mean absolute error. Now, once again, this is the simplest way, but to measure the performance. But again, remember, no single metric will give you comprehensive idea of the model performance. You need multiple metrics. So that's the reason why a second popular metric is called RMSE. So RMSE is the same RMSE that you would have encountered in your study of chemistry, physics in your elementary school. So it stands for root mean squared error. So the main difference is that you square the error here in this case and take before taking the average. In this case, we take the absolute value. In this case, we take the squared error. So that's the main difference. So what difference does the squaring make? So you must be wondering. So RMSE gives a relatively high weight to large errors. So if this error is large, then RMSE will blow it up like anything. So it is more useful when you want to minimize large errors. Now, the other question typically students get confused is what value of RMSE is good, right? So in classification and accuracy of 80% can be considered good, 90% can be considered good. But in case of regression, what value of RMSE is good? So that is very relative to the domain of the predicted value, right? MAE or RMSE are very specific to the domain. For instance, if you are predicting a stock price, even $5 may be bad, right? A prediction error of $5 may be really bad. But if you are predicting a house price in, say, the Bay Area, in where I live, in San Jose and California, even $10,000 may be okay, even if you are wrong by $10,000, because that's typically happens for various reasons. $10,000 is not too big a difference. So it all depends on the domain. So there's no absolute good RMSE, there's no absolute good MAE. So there's another metric called residual standard error, RSE. It is the same as RMSE, except that instead of this n here in the denominator, we have n minus 2. So there are some statistical reasons for that. We are not going to cover that reason. So the reason it's called residual is because it's the difference between the ith observed response and the ith response value that is predicted. So it's a bit confusing. We'll cover it in a little more detail later, but I just wanted to introduce that idea also. So residual standard error is the average amount that the response will deviate from the actual or the true regression line. So, okay, let us look at the difference that RMSE makes, right? So if you look at this slide, the mean average, so in this case, the errors are evenly distributed in case one. So the error is 2 uniformly across all predictions. So the stock price was predicted $120 and the real price was $122 for this first stock. Another stock, $92 and the real price was $90, so on and so forth. So the error was uniformly 2 for this machine learning prediction. So if you look at the MA, obviously it will be 2 and the RMSE is also uniformly 4. But look at the difference in when the error is large. So in under case 3, right hand side, the error is 0 for most of the predictions, but for the last prediction, the error is 20. Right? When the error is 20, The MAE is the same because only one instance was predicted incorrectly. All the instances were predicted correctly. If you look at the mean average error, it is 2. But if you look at the RMSE, it is 6.325. So that is the difference it makes. From 2 and 2, you jump to 2 and 6.325. Right? So that is the difference that RMSE makes. If the error is small, in this case, the error is 1 uniformly and for the first 5 instances, and for the remaining 5 instances, it is 3 uniformly. In such cases, RMS does indicate some advantage of using it, but essentially they are more or less the same. So RMSE makes a difference. Now, more than RMSE and MAE, machine learning uses a metric called R squared error. So R squared error so to understand R squared error, we need to understand a few things. One is the total sum of squares, and the other is the residual sum of squares. Right? We talked about this concept of RSE. RSE is an absolute value. Anyway, let us talk about TSS and RSS. So TSS is given by the difference of the actual values from the average. Remember, this bar means average, hat means predicted value. So TSS is the difference between the actual values from their average. So that is the total sum of square. And on the other hand, can you guess what the residual sum of square means? So the answer is instead of bar, we have a hat. So why wears a hat instead of a bar? That's it. So it is a difference between the actual value and the predicted value squared. So we sum it all up, we get the residual sum of squares. So, so what does TSS indicate? It indicates the inherent variability in Y before applying any model. So by default, the class has this, suppose we'll take the example of a class of students. You pretty much know from their, they are in their third semester, for example. From the first semesters, you pretty much know the variability in the scores of the students, right? So total sum of squares captures that kind of inherent variability in Y before the prediction, right? So the inherent variability is the difference between what is observed and what is the average of the observed values. So that is the inherent variability. And the residual sum of squares measures the unexplained variation after applying regression. So that is the idea of unexplained variation. So this was very clearly explained based on the average, but this is what the model tries to explain um, uh, by its own behavior, right? So the unexplained variation after applying regression is this. So R squared is given by this formula, TSS minus RSS by TSS. So it is 1 minus the ratio of RSS by TSS. So R squared is the proportion of variance of Y explained using X. So Y is obviously going to vary, right? You call it a class of students, but the students vary quite a bit in the class. So the variance can be explained using average. That is one way. The variance can also be explained by applying a machine learning model. That is the other way. So R squared is a proportion of variance in Y explained using X based on the characteristics of the students. If you are explaining the variance, then and you only consider the proportion, then it's called R squared. So if R squared is equal to 0, then not much of observed variation is explained. That means the model hasn't performed good at all, right? Um, so you can think of TSS, this numerator, TSS minus RSS, as the amount of variability in the response that is explained. So this is what has been explained. And the ratio of that with the TSS is basically R squared. That's what it means. So how much inherent variation has the regression model eliminate? That's what is explained by the model, right? So without regression, we would have simply modeled the data with a y bar, right? With an average. So how do you determine the class? How do you tell whether the class of students has performed well or not? You just take the average. That is without using any machine learning models. So the better way of modeling the class is by using a machine learning model. So that's what this R squared measures. So uh, so once again, R squared value also depends on the domain, but we have a better idea of the model based on the R squared values. So if it is 0, we know that the model is may not be correct, or inherent variability is very high. Uh, Remember, for machine learning to work, y must be dependent on x. There must be some dependence between y and x. Otherwise, machine learning models make no sense. Y is the last column in the training data set, right? So there should be some some dependence of y on x. Otherwise, it does not make any, applying machine learning model does not make any sense. So if R square is equal to 0, that may mean that there is no dependence of y on x, right? So that is other point to remember. Uh, so so if we don't have any machine learning model, we would have modeled the class of data, the table of data with the average, right? Average of the scores. But if we have a machine learning model, we are in a better position to model the data, right? This is a regression line which models the data. With this line is representative of all the data points generated, data points in the data set, right? So R square kind of measures how well this line, which models the regression, which models the points, is compared to the average, right? Which is the default model. So how better did our regression procedure do? So that's what it means. Okay, so the other regression metric is F statistic. Uh, F statistic helps in particularly helpful in multiple linear regression, where I mean linear regression and multiple linear regression. So if there's only one variable, it's called linear regression, and if there are multiple x variables, it's called multiple linear regression. So F statistic is given by this formula, TSS minus RSS by P divided by RSS by N minus P minus 1, where P is the number of predictors or features or columns. They all mean the same. And it measures the relationship between X and Y. Once again, just like um, the correlation coefficient or the um, correlation coefficient is the simplest way, but we want more advanced ways, right? So if f is equal to 1, then there's no relationship. Otherwise, oh, by the way, n is the number of data points, right? I hope you got that. Uh, so if f is equal to 1, then it means that there is no relationship. Typically, it should be greater than 1, right? So the null hypothesis, again, this statistics parlance. So the null hypothesis assumes that there is no relationship between x and y. So to disprove, to reject the null hypothesis and say that there is a relationship, we need even small number of data items. I mean, for a small number of data items, we need a large F. So F should be really very high to reject the null hypothesis if the data set is small. But if the data set is large, right? If the data set is large, then even small f, which is greater than 1, is enough to establish a relationship between x and y. X are the features, the columns. Y is the last column in the training data set. So that is the idea. Uh, so that is also one of the reasons why we want more data. So the more the data we have, even small increment in f will be enough to reject the null hypothesis to establish a relationship. So it is called f because it follows the f distribution. You must be knowing about f distribution when the null hypothesis is true and the errors are normally distributed. Right, so that's the assumption. Now I think I have taken substantial time, so I will probably refer you to explainability. So the reason for so we covered a lot of machine learning models, right? But these metrics are still not enough, and that is what we proved in this paper. So this paper, which was published recently, um, proves that merely achieving superlative evaluation metrics can be dangerously misleading and may infringe upon ethical horizons. A future direction is to investigate methods to quantify the effectiveness of machine learning models in terms of insights from their explainability. So what we did was we took a popular machine learning data set for predicting mental health of people. So there is an organization which conducts surveys every year for I think mostly employees working in the software industry, I believe. So they ask them a lot of questions and then they create these data sets every year. So a lot of researchers have used that data set and achieved superlative performance like 90s, and they are able to predict they claimed to predict mental health issues with 90% plus accuracy, multiple papers. So we took that data set and we applied explainability techniques. So we tried to explain the behavior of the model. And what we found was very surprising. We found that the models were doing something totally meaningless. Like in one instance, the model was predicting that the person does not have mental health issues. Um, Even when in the survey, the employee said that he is taking time off for mental health, for coping up with mental health issues, right? So that's things like that. I don't exactly remember the specific instance, but things like that. The models were doing something very mischievous. So that is risky, right? I mean, you predict something, mental health is a very serious issue. When you use machine learning models to predict mental health, and if they make these kind of mistakes, it's a serious issue, right? So that is the reason why we said that just performance metrics are not enough. You need to also watch for explainability aspects of the. So they're focusing on temporal differences. So and then so I explained all this explainability. Probably not, right? And other stuff in this. When we change it to 921, right? Certainly, or if the income is 30,000, we change it to 35,000. So we make such changes and generate these points. YouTube channel. So we generate a diverse data set that simulates. You can watch this to understand the importance of explainability when evaluating model performance. So that's all I had for this talk. I know I extended my time quite a bit, but hopefully you found it interesting. And for those who dropped out and who could not join on YouTube Live, I could not start YouTube Live. I will try to make the video available online somewhere. And you can stay in touch. I'm on social media and on the internet quite a bit. So please feel free to stay in touch, and I'm open to any questions that you may have. Maybe one or two questions. Any questions? Okay, there's a question on the chat. You mentioned an academy. Sorry, in what context? Academy, I'm not sure what exactly. I mean, I don't. I must have said University of Bolton. So this video that I showed is on University of Bolton's channel. That's what I. They have a series called November to Remember series. So I gave an inaugural lecture there. Oh no, I don't have an academy. I'm just associated with IEEE. I'm the chair of the IEEE Silicon Valley chapter, and I also am a faculty member of Applied Data Science in San Jose State University. Sorry. Okay, what evaluation metric do you recommend to evaluate the performance of object detection segmentation of food items? The dataset is fairly balanced with 32 classes. Do you recommend MAP, RUC, MCC, and others? So my suggestion is to be very comprehensive when evaluating models. In fact, that's what I tell my students. Every semester they do a course project, and I tell them to evaluate the models that they used with as many metrics as possible, and if possible, include explainability also into it. Uh, so I wouldn't depend on any single metric to evaluate a model completely. I mean, to give an indication, you can just start with accuracy, area under the ROC curve, things like that. But if you want a comprehensive model evaluation, I would recommend you to incorporate all the metrics that we talked about, all the most of the explainability techniques that are available, and also include some fairness metrics. I know I did not cover fairness in this talk. Maybe for future talk, I'll reserve that. But even fairness metrics can be considered. So for context, I'm comparing the performance of three models on the same data set. Exactly. So that's what I said, right? Like I mentioned, the models vary substantially. Like in the ROC curve plot, we saw various points, right, in this slide. Um, we saw various points. These are all different models. So ROC will give general idea, but it needs to be corroborated with several other metrics. So that is the idea. Okay, any other questions? This was great info. Thanks. Awesome. Thanks so much for your insights. And anything on the question panel? So this is oh, I did not. Okay. So thank you all for your patience and nice questions. Thanks for making it interactive to the extent possible. I will try to make the video and the slides available on the internet. And once again, thanks for taking your time to attend this. See you all in a future talk. Bye.